Question 1. Present the proof of Cayley's theorem. Cayley's theorem says that every group is isomorphic to a group of permutations. Permutation group is a group of permutation on a set, and permutation on a set means bijection of a set to itself. The corollary is every finite group G of order n is isomorphic to a subgroup of symmetric group Sn. In order to prove this theorem, we have to understand the definition of left regular representation of set G. To define this term, let G be a group. The function phi maps group G to the symmetric group Sg is defined by phi x equal to lambda sub x, where lambda sub xg is equal to xg for all the element G in the group G. In order to be sure that lambda sub x is a permutation, it should be verified that lambda sub x is both one-to-one and onto. To show that lambda sub x is one-to-one, we let A and B is an element of group G. Then we will get lambda sub xa equal to lambda sub xb. Then we will get xa equal to xb. And by cancellation, it will give A equal to B. Next, we need to show that lambda sub x maps onto group G. For any element B in the group G, we will get lambda sub x inverse times B equal to x inverse times B, and we will get B. With this, it is verified that lambda sub x is a permutation. We are now ready to prove Cayley's theorem. Firstly, let G be a group. The left regular representation shows that a function phi maps group G to the symmetric group Sg is defined by phi x equal to lambda sub x. Then, to prove the Cayley's theorem, we need to verify that phi is one-to-one and that phi is a group homomorphism. Firstly, we need to verify that phi is one-to-one. Suppose that A and B are elements in group G and phi A equals to phi B. Then, from the definition of left regular representation, we know that phi A equal to lambda sub A and phi B equal to lambda sub B. We write lambda sub A equal to lambda sub B, which is also the same as lambda sub A E equal to lambda sub B E, where E is the identity element. Then, from that, we get A times E equal to B times E, and cancellation gives A equal to B. Thus, we have verified that phi is one-to-one. Next, we need to verify that phi is a group homomorphism. Let A and B be elements in group G. Then, phi A times B equal to lambda sub AB, and phi A phi B equal to lambda sub A times lambda sub B. To show that these two permutations, lambda sub AB and lambda sub A times lambda sub B, are the same, we let G be an element in the group G. From the definition of left regular representation, we know that lambda sub ABG is equal to AB times G, which is also the same as A times BG. Again, by left regular representation, we get A times BG as lambda sub A times BG. We will get lambda sub A times lambda sub BG, which is also equal to lambda sub A lambda sub BG. So, we can see that lambda sub AB equals to lambda sub A times lambda sub B, which implies phi AB equal to phi A times phi B. Thus, phi is a group homomorphism, and this completes the proof of Cayley's theorem. Please note that we could have used the right regular representation to prove Cayley's theorem instead of the left regular representation. Question 2. Show by example that integer modulo 7 is isomorphic to a group of permutation. From Cayley's theorem, we know that every finite group G of order n is isomorphic to a subgroup of symmetric group Sn. First, we consider the Cayley table of group integer modulo 7 with elements 0, 1, 2, 3, 4, 5, and 6. We can see here the Cayley table for integer modulo 7. It is important to make sure that each element of the group must appear once and only once in each row and each column of the table. Guided by the proof of Cayley's theorem, we define subgroup hash with elements from phi sub 0 until phi sub 6, where each of the element represents a permutation. From the table, we get phi sub 0 equal to the cycle notation 0, as all the elements of the integer modulo 7 maps to itself. For phi sub 1, we will get cycle notation 0, 1, 2, 3, 4, 5, and 6, as 0 maps to 1, 1 maps to 2, 2 maps to 3, and so on. For phi sub 2, we will get cycle notation 0, 2, 4, 6, 1, 3, and 5. Next, for phi sub 3, we will get cycle notation 0, 3, 6, 2, 5, 1, and 4. For phi sub 4, we will get cycle notation 0, 4, 1, 5, 2, 6, and 3. For the permutation of phi sub 5, we will get cycle notation 0, 5, 3, 1, 6, 4, and 2. And for phi sub 6, we will get cycle notation 0, 6, 5, 4, 3, 2, and 1. Then, these permutations can be converted to the standard notation of symmetric group of elements 1 to 7, as shown in the video. Thus, integer modulo 7 is isomorphic to the subgroup H of 7th symmetric group, where the elements of subgroup H consist of the cyclic notation of phi sub 0 until phi sub 6.